All right, let's get into it. Have you ever really thought about what happens when you hit enter on a SQL query? You know, it feels like magic, just instant. But behind the curtain, that query of yours is kicking off this incredibly complex, hidden journey. So in this explainer, we're going to be its shadow. We're going to follow it step by step and really understand how a database thinks. And, our story, our investigation, it almost always kicks off in the exact same way. It doesn't start with a piece of code. Nope. It starts with a feeling, a complaint that, well, if you've ever worked with software, you know it all too well. There they are, the 4 words that can ruin a developer's day. The application is slow. This is our signal. It's the smoke that tells us there's a fire somewhere in the system. And 9 times out of 10, the arsonist is something we call a bad SQL query. But what does that even mean?
Right, so what actually makes a query bad? You might think it's one of those super long, complicated queries with tons of joins. But that's not it at all. The real problem? It's about something else entirely.
It all boils down to one word: efficiency. A bad query is just a resource hog. It's like, imagine using a massive cargo ship just to deliver a single birthday card. Yeah, the card gets there, but the cost, the fuel, the crew, the time, it's completely out of whack. That's our bad query, burning through I/O and CPU. To find out why, we have to trace its steps. So let's put on our detective hats. We're going to trace the secret journey our query takes from the second it hits the database. This journey has 4 critical stops, and a slowdown in any one of them, well, that's what causes the problem we're trying to hunt down.
Here are the checkpoints. First, parsing, then optimization. After that, row source generation, and finally, execution. Every single query has to go through this process. We're going to focus on those first 2, parsing and optimization, because that's where the real high-stakes decisions get made.
So stop number 1, parsing. This is where the database basically does a grammar check on your code. But more importantly, it asks itself a question that changes everything. Hey, have I seen this exact query before? And the answer to that question sends our query down one of 2 very different paths. If the answer is yes, boom, we get what's called a soft parse. This is the express lane. The database finds the old plan, reuses it, and it's super fast, super efficient. But if the answer is no, we hit a hard parse, and that is a performance killer. The database has to stop everything and build a brand new execution plan from scratch. It's slow, it eats up resources, and it's public enemy number 1 for performance. That hard parse forces our query into the most intense, the most interesting part of its entire journey: optimization. This is where the database really has to put its thinking cap on. We are now heading straight into the brain of the operation, the cost-based optimizer. Honestly, the best way to wrap your head around the optimizer is to think of it as a super smart GPS for your data. You give it an address, the data you want, and its one and only job is to calculate the absolute fastest, most efficient route to go get it from the millions or even billions of rows stored in your tables.
And that's the big question, right? For any non-trivial query, there could be dozens, even hundreds of different ways to get the data. Should it use this index, or maybe that one? Or just read the whole table? Should it join table A to B first or B to A? With all those options, how on earth does it pick just one and call it the best? Well, it doesn't guess. And it doesn't have a favorite route. It makes its decision based on cold, hard math. For every single possible path it can come up with, it runs a specific calculation. And for each of those potential routes, it generates a single number, a score. It might look something like this: 1,482. This number has a name. It's called the cost. The optimizer's logic is dead simple. The plan with the lowest cost wins. Period. But what is this number? What is it actually measuring?
And here is the single biggest misconception about how this all works. That cost, it is not time. It's not seconds, it's not minutes, it's not anything you can measure with a watch. It's an internal, abstract number that represents the total work, the estimated CPU and I/O that a plan is going to require. So a lower cost just means a more efficient plan.
So how does it come up with that cost number? Well, it all boils down to making 2 incredibly important guesses.
First is cardinality, which is just a fancy way of asking, how many rows do I think I'm going to get back? And second is selectivity. What percentage of the table do I think I'll have to read to find them? Getting these two guesses right is everything.
And that brings us to the final and maybe the most critical piece of this whole puzzle. If our optimizer is a GPS and its calculations are the engine, what is it using for a map? How does it get the information it needs to make those vital guesses?
And here's the answer. It's one word: statistics. See, the optimizer is born knowing nothing about your data. It relies completely on a set of statistics that describe your data, things like how many rows are in a table, how many unique values are in a column, is the data skewed. These statistics, they are the optimizer's map of your data.
So what happens when that map is out of date? Well, with stale statistics, the optimizer's guess can be catastrophically wrong. It might look at its old map and guess that a query will return, say, 10 rows. But in reality, the table has grown, and the query is actually going to return 1,000,000 rows. Based on its bad guess of 10, it picks a plan that is horribly inefficient for handling the 1,000,000 rows it actually encounters.
And that, right there, is the root cause of so many performance mysteries. It's a simple chain of events. The statistics are old or just plain missing. This leads the optimizer to make a bad guess. That bad guess leads to it choosing a bad plan, and that bad plan is the bad SQL that made our user complain in the first place.
So, we've done it. We've followed the journey all the way from a vague user complaint down to a very specific cause, a bad decision, made by the optimizer because it was working with an old, outdated map. And this gives us our next big clue in this investigation. We know the optimizer chooses a path and creates a map for the query to follow, what we call an execution plan. So the next logical question for us as performance detectives is, how can we get our hands on that map? How can we read it ourselves to see the exact route the database chose? And that is a fantastic question and exactly what we'll be breaking down in our next explainer.